In that case, we are ready to start section 3.3. 3.3 is working with your measures of variation. Variation is also called the spread or dispersion. You're trying to find the degree to which the data are spread out. So we're trying to find a way to quantify whether or not everything is really close together or whether things are really spread out far, because that makes a big difference in what you know about it. So one of the ways that we can measure the amount of variation that there is the range. The range of a set of data values is just the difference between the maximum data value and the minimum data value. So if we were talking about test scores, and I told you that the range was 5%, that's telling you that the difference between the highest grade and the lowest grade was 5%. On the other hand, if I told you that the range between the grades was 60%, then that's saying the difference between the highest grade and the lowest grade was 60%. Huge difference in the spread of that data then, if you're looking at everything being really close together versus everything being spread apart. They might both have the same mean, finding that same center. So both of them might have a mean of 80%. Well, saying that the range is 5% says, well, you're only looking at a difference of 5% above and below that 80. So everybody was really right there at the 80% mark, or right close. Versus if I said that the mean was 80%, but that the range was the 60, well, that may be everywhere from a 40% to 100%, or from a 30% to a 90%, or something along that lines. That's a big difference between stuff, and still saying that the mean is 80 both times, still telling you a lot about that data. So range is one easy way to look at things, because a lot of times it's pretty quick to find that maximum and the minimum and just see what that difference is. But it doesn't tell you a whole lot about it. The round-off rule for measures of variation: when rounding the value of a measure of variation, carry one more decimal place than is present in the original data set. So round only your final answer. Do not round the stuff in the middle. Now, obviously with range, when you're subtracting two numbers, there is no round-off rule. Because when you subtract two numbers, you're just going to get the number rounded the same number of decimal places. But we're getting ready to work with finding the standard deviation and the variance, and those two have a lot of calculations. Don't round in the middle. Save it till the very end, and then round to one more decimal than what we have. So standard deviation. Standard deviation of a set of sample values denoted by S is a measure of the variation of those values about the mean. This is a way to measure and see how close is everything to that mean. How much do they vary away from where you know the center is? And we use S for standard deviation. This is the formula for the standard deviation. Standard deviation is the square root of the sum of the differences between your data value and the mean, because this is your sample mean, squaring those values, adding all those up together. After you add them all up, we're going to divide by n minus 1, where n is the number in your sample. Now, formulas, let me mention that one again. I don't expect you to memorize this formula. I expect you to be able to use the formula. I don't expect you to be able to memorize them. You've got your little formula sheet. I will give you guys one similar to this. Mine's just printed out, though. If you don't have one of these in your book, it's on Blackboard under content. I think I call it reference sheets, I think what I call it. Print that out, because that'll give you an idea of what you can use, so that as you're practicing doing things, get familiar with where things are on here. One you're going to need right now is this very first little block is where we're finally at, which is your chapter 3, which is your descriptive statistics. It's already got the formula for mean, which hopefully you guys already knew that one. But mean from a frequency table, and then we've got our formula for standard deviation. And so those are on there for you guys to be able to refer to and be able to use. So don't expect you to memorize it, but I do expect you to understand what it means and be able to do it. On the other hand, if it's a population, the formula for the population standard deviation, first of all, population standard deviation is sigma, and it is the square root of the sum between the sample, or the data values, minus the population mean. Subtract those values first, then square them, adding all of those, it's called the sum of the squares by the time you do that. Divide the sum of the squares by capital N. N is the population, the number in the population. We do not subtract the 1 from the population. Then once you do that, take the square root of that answer. And having that subtracting 1 for sample data versus not subtracting the 1 for the population data comes from looking at how to get that accuracy and doing those calculations that we don't get to get into where all the formulas come from as much as being able to use them and understand what we have found when we do. So if we are looking at some data, and this is the first time I'm trying to use these, so I'm hoping that these work out nicely as we come out doing these. But if we have some data, and let's just say this is the percent of seeds that are germinating. So we've got brand A, and we're going to have brand B here in just a little bit. So this is telling me that out of the different samples that we've taken, 95% of the seeds that were in that sample germinated versus 94%. So these are the different things. First of all, what's the range on this data? Okay, why is my range 6? Okay, 96 minus 90. So there's that 6% difference. In this case, the percents really aren't the piece to keep track of. Just recognize that there's a difference of 6, although these stand for percents. If I'm going to find the standard deviation, and I didn't put the formula on here. Standard deviation, is this well, let me tell you differently. This is a sample, so this is not taking all possible seeds and all possible groups of these seeds. This is a sample of seeds that we had. So we were taking groups of, I don't know how many seeds might have been in our different samples, finding what percent of those germinated. To find your standard deviation, which will be the lowercase s, it is the square root of the sum of the difference between the sample and the mean squared divided by the n minus 1. Well, order of operations, got to take it piece by piece by piece. First thing I need to do, I need to find what is the difference between the values and the mean. Well, before I can find the difference between the values and the mean, I need you guys to find the mean. So find the mean of this data. And by the way, on these, I do want you guys to be able to do them both with the calculator and without. Now, when I say with the calculator, I'm going to show you guys a calculator shortcut to do all of this work quickly in like 2 steps. But I want you also to be able to use the formula. And tonight on the homework, you'll have to do a problem where you have to do these piece by piece using just the formula. And on the test, I think I'm going to have a problem on there that you have to do by hand. Yes, test is Friday. Once you have your percents, put those on your board so I can see where you guys are at. So what did we get for the sample mean? Okay, we should be getting 93. When you add them all up, what are you guys getting? 651. So taking the 651 divided by 7 tells you that the sample mean is 93. Okay, so now that I know the sample mean, the next thing I need to do is to figure out, okay, so what I'm trying to find in standard deviation is a numeric way to say what is that variation? How far away from the middle is everything? So I need to figure out how far away from the middle each value is. So you're going to take the sample, the data value, minus the mean. So I'm going to take the 95 minus the 93. So I'm just going to have 2. 94 minus the 93. So we'll have the 1. 93 minus 93 is 0. 92 minus 93 is what? Negative 1. I'm going to let you guys, no, let's just finish that. 96 minus 93 will give us 3. 91 minus 93 will be a negative 2. 90 minus 93 is a negative 3. Now, the thing is, if I just added all those together, they're going to cancel out because we're talking about some of the values are above the mean, some of them are below the mean. And if it's the mean, and if you found the mean correctly, it's in the middle. And so if you added all these things together, that's 0. That doesn't tell me anything. I need to go through and find a way to mathematically get rid of all those signs. That way we can use those as a comparison. There's one way we could do is just drop all the signs, but it's easier and more helpful and giving us a better way of doing things and the way the standard deviation comes about is to go through and square each value. And so if I go through and square each value, the 2 squared becomes the 4, 1 squared is 1, negative 1 squared is 1, 3 squared is 9, negative 2 squared is 4, and negative 3 squared is 9. So I'm just going through and squaring each data value separately. Now if I added all those together, they're not going to add up to being 0 because by squaring them, the signs have disappeared. We're guaranteed to have a positive number for each one of those at this point in time. Now if you're using your calculators, you may have to make sure you put parentheses around things so that you're squaring the whole entire value. That way you are squaring both the negative and the 2 and not getting a negative number as you do that. Now, if we look back at our formula, the next thing we want to do, so we've done this middle part, the x minus the x bar, x minus x bar squared for each piece. This is telling me to add all those together. So what do we get as we add all these together? So 10, 20, 28. That's now my numerator. If you continue using statistics much, this is also called the sum of squares. We're creative and stuff like that. Sum, because you're adding all these together, and it's of all the different squares, or you're finding that difference between the square, the difference between the values and the means. So sometimes called the sum of squares. I won't be using that term on anything that you have to remember. So that's our numerator. Next thing we need to do is to divide that by n minus 1. So the sample size minus 1 value. We're going to take that the 28 divided by the n minus 1, so 6. And what is 28 divided by 6? 4.6 repeating. Okay. And then take the square root of that. Now with the square root, you can, so you don't have to do things in there. You can hit second and enter to get it to use the number before. So what you guys have done so far, you have the 28 divided by 6 to get, oh, I'm a little close, to get that 4.6 repeated. If you hit second and enter, which enter is, I guess you know where enter is. Oh, I just hit the wrong thing. Sorry. Second and answer. The answer is right above the negative. I just hit the wrong thing. Second and negative, to take that answer before, I need to have the square root first. Second and square root, and then second and answer. Then it just takes that number from before, so you don't have to find the square root and type in 4.6 repeating. Because again, we don't want to round too much too soon. Questions on where I found things, considering I kept trying to hit the wrong buttons. But that A and S takes the answer from before, and then it continues using that number. So now we're getting the standard deviation to be 2.16. Oh, actually, I guess we'll end up rounding it to 2.2. So we had the 2.160, whatever the numbers were, which would be approximately, and we would round that to one more decimal than what we had, so we're going to round that to 2.2. So standard deviation in this case is 2.2. So this is a measure of how close all these values are to the mean. So what we know about this is that we know for seed A, the mean amount of time or the mean amount of seeds to germinate is 93% of the seeds. And we know that it has a standard deviation of 2.2. We're going to talk more about what that standard deviation is telling us, but it has a standard deviation of 2.2. Some important properties then of what that standard deviation really is telling us. First of all, the standard deviation is a measure of the variation of all the values from the mean. So we took and used every single number to compare how far it was from the mean. we did not just use the two extremes like we do for range. Every single data value is a piece of trying to calculate out the standard deviation. The value of the standard deviation S is usually positive. The only time it's not is if there is a standard deviation of 0, if every single value is the same value. So if from our seeds, 93% of them germinated every single time we did it, then the standard deviation would be 93. But that doesn't happen too often in real life situations that you get your standard deviation of 0, that everything fits to being the exact same thing. If I was to try, if we were trying to find standard deviation of student ages, if every single person in the classroom was 20 years old, then we would have a standard deviation of 0. But if we have anybody that's a little younger or a little older than 20 years old, then we now no longer have that standard deviation of 0. And so that is a calculation of figuring out how far from that mean we actually are. The value of the standard deviation S can increase dramatically with the inclusion of one or more outliers, which is the data values that are far away from all the others. So those outliers have a big influence on your standard deviation, which standard deviation is a way of measuring, are all the values close to each other or are they really spread out from one another? And so having that would be a piece of, having that outlier would really say, well, we've really pulled things away from it. And it's drastically increased it. I guess what I do want to go back, make sure you recognize you will never have a standard deviation that's negative, which if you think about the formula, you're squaring numbers, that will make them positive. Square roots are always positive, so there's absolutely no way that you're going to have a negative standard deviation. Also, the units of the standard deviation S are the same as the units of the original data values. So our original data in our case was the percent of seeds that were germinating, so our standard deviation was that 2.2% of the seeds germinating. The standard deviation would be that 2.2%. If we want to use, and I'm not wanting to use this data, to figure out how to use the calculator and do it. Those are the steps, but I want different values to use this time. I'm comparing different data than I have done before in the past, and so I wanted to kind of look at it a little differently. If we use our calculators to do this, now, as I said, I want you to do some of it by hand, but then I also want you guys to be able to use the calculators to do it. First thing we have to do is to put the data in there. So if you go to Stat, under Edit, so just hit Enter on Edit, I want you to put those in for List 1. And so these are the data values on this first one that I do want you guys to put in. The data values I wrote down and the data values I have here are the same. I think I wrote it down before I fixed it. We'll hope for that. So having in that 95, 95, 99, 93, 84, 99, and 81. So list 1's all you have to worry about. I've got my other data in list 2 so that I didn't have to do it all by hand as I was trying to get my numbers to work. So everybody got that in list 1 now? Okay, now go back to Stat again. Go over to Calculate. And we're going to calculate the one variable statistics, which is that very first one. So you can just hit Enter on that first one. Now, if you have it in list 1, you can just hit Enter. If you had it somewhere else, you've got to tell the calculator where you have it. So to do that, if I had it like my other ones in list 2, I would hit second and number 2 to get list 2, because L2 is right above number 2. I don't want to do that right now, though, because I want to look at the statistics of list 1. So that when you hit Enter, and you could hit second and 1 to tell it list 1, you just don't have to. What it's telling me then is a lot of the information about this this the sample data. We have the mean. Mean's 92.28. I wanted the other data value. I had to fix it. Okay. I want you guys to go back and fix it because I want everybody to have the same thing. Go back to stats, go to edit, and do list 1 as being 100. I don't know why it got changed before. The 100 is what I want it to be. Yeah, the first one to be 100. So whatever was there, delete that out and put in the 100. So everything else is just staying the same. So if you hit 100, enter, and you're good. Yes, Sarah? Okay, let me fix him. Then go back over to stat, arrow over to calculate, and then do the one variable statistics. I know. Okay. So now you've got it back. Right now yours is in list 2. So go back to your stats, arrow over, calculate, and I hit second list 2. Okay, so now when we do this, we get our mean to be 93. So X bar is sample mean. Now, keep in mind, if you are working with a population instead of a sample, that you have to remember that sample or the population mean is the mu, which is that Greek letter looks like a U. But this is a sample, so our sample mean is 93, which I wanted both of those to have sample means of 93. That's the reason why I fixed that. My standard deviation, we have S sub x and we have sigma sub x. S sub x is saying the standard deviation of the sample. Sigma sub x is saying it's the population standard deviation. So you have to recognize, am I working with a sample or am I working with a population? Because the formulas are different. And as you can see, our numbers are slightly different when we're comparing those. In this case, our sample standard deviation should be the 7.637, so 7.6. Okay, questions to hear? So with both of these, if we're comparing these, well, let's discuss. So there was my data. I guess I could have had that be listed there to show you guys what the data was. So when we just found this one, we found the standard deviation to be the 7.6. Standard deviation is telling me how far away from the mean it is. Would it be better to have a large standard deviation or a small standard deviation? You're wanting it to be small. If you're the one that's buying the different seeds, and we looked at having this data is the one we just had, the data we had before, and so both of them have a mean of 93. The first one had our standard deviation of 2.2. This one has the standard deviation of 7.6. It's telling me how closely those values are to each other. Just common sense as you're looking at it, if you're buying a bunch of seed and you're going to have lots of bags that you're planning on planting in your field, would you rather have, if they're both comparing, you know both of them have a 93% mean number of seeds that come up, small standard deviation is going to be a lot better for you. Because now we're looking at having all of our data is pretty tightly packed around that 93%, versus here, we might get as good as 100% of them come up, but we might be as low as 81% of them come up. And so depending on which bags you're lucky enough to get, you can have a wide variety of what you're looking at. And so trying to get that data value close gives us a lot of information about it. And so depending on what you're going to be using that for, it's going to be helpful to be able to look at stuff. What was that, Aaron? I just randomly picked numbers out of my head because I wanted to have means of 93. I'm not blaming you there. I'm just letting you know it's really not accurate whatsoever on these numbers this time. I try a lot of times to use accurate numbers, and I did go back and look to see what the actual percents, and they said most are above 90%, the good ones are above 95%, but I didn't. Not at all. Okay, if we looked at this one, this is another problem that I've come across that's also dealing with these. If we were comparing, and these are populations of outdoor paint, so they're creating new type of outdoor paint. They only created 6 gallons of each one of those. If we're looking at trying to compare which consistency would be the better consistency. Both of these have, it's comparing the amount of months until it starts to fade. And our first data values, let me show you what the actual data value was. So brand A might start to fade in 10 months, 60, 50, 30, 40, or 20 months. Brand B, 35, 45, 30, 35, 40, or 25 months. So as you're trying to compare these, just by glancing at them, which one can you see has the bigger standard deviation? Okay, A has a bigger standard deviation. Just looking at the range alone, ranging from starting to fade in 10 months or starting to fade in 60 months, compared to starting to fade in 30 months or lasting up to 45 months. Both of them have means of 35 months. So they both, if you're going to the store and you're getting ready to buy paint, they're going to say, well, both brands are going to last an average of 35 months until they start to fade. So you're looking at, okay, I should have, probably around 3 years until I have to worry about the paint starting to look like it's fading a little bit. But when you start looking at the data, if you buy brand A, you might be the unfortunate one that it only lasts 10 months until it starts to fade, or you might be lucky enough that it might last for 5 years till it starts to fade. That's a pretty big variety between those two. We can see that this one's actually got a nice uniform distribution because they're pretty evenly spaced as you go, with that mean of 35 being smack dab in the middle. On the other hand, if you buy brand B, you've got a lot more consistency among what you're going to be buying. It might last only 25 months. It might last up to 45 months. So you are looking at a range in there, but it's a lot more tightly packed that you're not getting those extremes on it. And if you calculate out the standard deviation, and before I've had us do the standard deviation on these instead of my corn seed. And what did we come up with my standard deviations? Trying to find where the numbers are. One of them's 29 and the other one's something else. .5. So you're looking at having a standard deviation of wrong one. The bottom one being the 6.5, the top one having a standard deviation of 17.1. So again, a much larger difference between those kind of standard deviations. If we look at variance, so again, these are measures of trying to figure out how much variation there is between things. The variance of a set of values is a measure of variation equal to the square of the standard deviation. So before you take the square root, you had the variance. So earlier when we were doing our problem, a lot earlier, when we were here, when we had that 4.66 repeating, that was our variance. So in this case, s squared was the 4.6 repeating, which would round to the 4.7, would have been my variance. So your sample variance is S squared, is the square of your sample standard deviation. Again, make sure you find it before you start rounding. If you take our 2.2 we had and we square it, you're not going to get the exact right value because you've already rounded that to the 1 decimal, and then once you square it, it really affects the rounding on those. Population variance is sigma squared, is the square of the population standard deviation sigma. So for the paint that I was looking at, I would have been dividing by just n instead of the n minus 1 because those were entire populations. And you would use the sigma. And again, if you were looking at it on the calculator, you would use that sigma x for the sample. Sigma x would be the population standard deviation. And you'd have to square that number. And if you're squaring that, if you use the calculator and do it, keep several decimals, square that, and then round those answers. Now, how does standard deviation help me? Standard deviation helps me because it's not a very good normal distribution. If I have a normal distribution, then what it's telling me is most values are going to be in that middle part. Most of the values, this is where my mean is. If it's a nice, perfectly normal distribution, my mean and my mode are both in the same place. And we're having values that are kind of going off in both extremes. Now, if I have it to where everything's really close, or, well, let's do it this way. Let's make this one a little less. If we had these two different distributions, they're both normal distributions. Both of them have the mean in the same spot. So in this case, if we were going back to our corn, they both have a mean at 93. The red one obviously has a lot less spread than what the green one does. And that's what your standard deviation is trying to figure out. Well, how much do those things spread apart? Are they really close to each other, or are they a lot more variation between those two things? And so trying to figure out where most of them lie, they're usually, if it's a good normal distribution, they're going to fall within 2 standard deviations of the mean. And so what that tells me is if my mean was right here, if I go 2 standard deviations above and 2 standard deviations below, that's where most of my values are going to lie, which is our usual number of values are going to lie. And so if we went 1 standard deviation, 2 standard deviations, well, I got to stay consistent. Just a second. Oh, I had erased more than I wanted. So if we do 2 standard deviations here for the red one, compared to the green one has larger standard deviations. So maybe this is 2 standard deviations for the green one. You're looking at having most of your values falling in that range. And so trying to find where you're going to get that same quantity, that the majority of those values to fall, is going to be within 2 standard deviations. So if we went with the first brand that we had, where we had the mean of being 93, and my sample standard deviation was the 2.2, what do we anticipate being the range of data values that most of our data values will fall within? What is 93 minus 2 of the 2.2s? Using your calculators, what do you get? And then if we take our mean plus 2 of our standard deviations, .97 what? Yeah, I'm pretty sure the 88.6 is right, though. Okay. So what this is telling me is it's usual for this brand to have between 88.6 and 97.4% of the seeds germinate. And so that gives me that range that I would anticipate that if I was going to buy seed, that I would anticipate that it's going to have between 88.6 and 97.4% of them are going to germinate. That would be the usual data values. Now, if we did the other one, I guess I should have used red on that one and then green on the other one. I used blue so it doesn't stay. If we did brand B had a mean of 93 and a standard deviation of 7 point what? 7.6? Is that what you had, Shelby? Okay. Couldn't remember what I had. Find what you think the usual values would be for that one then, and write those on your boards. All right, looks like for those of you that have it on your boards, we're looking at between 77.8 and 108.2. Now that's my usual range. Now, we got to make sure, because with statistics, it's not going through and, well, I guess I need to say it this way. With statistics, you got to make sure you use some common sense in the process of what you're doing. Why do I say that about this problem? It's over 100. What's wrong with being over 100? Okay, we're talking about the percent of seeds that are germinating. I'm not going to be capable of getting over 100% of them germinating. They're not going to like create extra seeds to germinate just because they're there. And so you know that for this problem to make any sense, this is really looking at 77.8% to 100% of those seeds are going to germinate. So with the statistics, it's looking at the calculations with the values, but you've got to take everything you come up with and use your common sense and use critical thinking to be able to figure out what's going on with those. Now, that's telling you what my normal, my usual values are going to run into. You need to remember that our usual is going to be 2 standard deviations from the mean. We're going to use that a lot throughout the semester, and we're going to build on why that comes and how it ties back to our normal distribution as we do, but that 2 standard deviations is important. Now, if it's 2 standard deviations away from the mean, 2 standard deviations below and 2 standard deviations above really means it's within 4 standard deviations of each other. The maximum and the maximum and the minimum of what would be usual is going to be within 4 standard deviations. That's why we have this range rule of thumb here. Range rule of thumb says to roughly estimate the standard deviation from a collection of known sample data, use the range, what is the maximum and minimum, what is that difference between those, and just cut that in 4. And that'll approximate the standard deviation. Now, the reason why you would sometimes want to do that, if I asked you, and I want you guys to do this, estimate what you think the standard deviation of NCMC student heights are. I'll just go with all students. I'm not even going to break it down to girls or guys because I don't know that you're going to make that much difference in your estimation. So if I'm trying to estimate this, discuss together what you guys think the maximum height is and the minimum height is. So what do you think the tallest person is in NCMC? 6, 7? Okay. So if we have somebody that we know of that's 6'7", so that is 79 inches. Okay, what do you estimate the shortest NCMC student to be? Got a guess of 4'10"? Anybody agree or disagree? 4'10", good? Okay. So that'd be 58 inches. So what is the difference between 79 and 58 inches? Okay, we're looking at 21 inches. If I take that 21 inches and divide that by 4, then we're going to approximate the standard deviation of NCMC students to be about 5.25 inches. That's given a good guess. Now, are we going to be right smack dab being right? No. Because we're doing the easy, just trying to find an easy approximation of what that range would be. And we definitely had our outlier because our 6'7" is definitely an outlier within this, and we knew what that outlier's height would be. And so that made a difference within things. And as we mentioned, those outliers definitely can skew what our data comes out to be in. But it still is giving us a good range of what to anticipate for that standard deviation. Now, the empirical rule comes back to that normal distribution. And we will refer back to the normal distribution a lot. Ooh, that's a really bad one. I'm trying to get to squeeze into my little space. So if we go back to our normal distribution, what that empirical rule is saying, for data sets having a distribution that's approximately bell-shaped, so approximately normal, the following properties do apply. About 68% of all values fall within one standard deviation of the mean. These are going to be numbers you're going to want to know. 68% of them fall within one standard deviation of the mean. So if we're going, got the mean here in the middle, if we go one standard deviation on both sides, we're saying 68% of the values fall into that range. Looking at that, I probably didn't go within one standard deviation on both sides. It's like that'd be a little bit closer. So a lot of the values are going to fall within one standard deviation. If I go out to 2 standard deviations from the mean, 95% of those values are going to fall within 2 standard deviations of the mean. When we're trying to find our usual values, we're going with 2 standard deviations. It's usual. 95% of the values falling within that. That's a lot. You've got your 5% of outliers is really all we're kind of ignoring when we go within 2 standard deviations of the mean. So that's the reason why we consider that usual. That's what you've got as your normal values, are those that are within 2 standard deviations of each end. Because if you're having a normal distribution, that's a lot of the values falling in there. Then if you really want to get better, go 3 standard deviations. 3 standard deviations away from the mean has 99.7% of the values fall within 3 standard deviations of the mean. So you're hitting almost everything once you do that. So again, those 3 numbers are going to be ones you'll want to memorize for the empirical rule, the 68, 95, and 99.7. So when we look at this, 68% are within 1 standard deviation, so 34% on each side of that. 95% within 2 standard deviations of the mean. 99.7% within 3 standard deviations of the mean. So you're really leaving off about 0.15% of the values on both extremes. And so those are your extreme outliers, are not going to be covered when you're within 3 standard deviations of the mean. Notice what you're taking is your value for your mean, and if you're trying to find that lowest value, you'll subtract off 3 of those standard deviations. Now this is if it's a nice normal distribution. Not everything's normal. Let's look at one more example while it is still normal. If we look at number 34 on page 113. On number 34 on page 113, it's looking at the empirical rule. The author's generic generator produces voltage amounts within a mean of 125 volts and a standard deviation of 0.3 volts. And the voltages have a bell-shaped distribution. Using the empirical rule, what's the approximate percentage of voltage amounts between 124.4 and 125.6, and then between 124.1 and 125.9? Well, if we look at what we know we have a mean of 125, and we know we have a standard deviation of 0.3. If I go one standard deviation below it, we get 124.7. That's not any of the numbers I needed. If I go 2 standard deviations below that, so if I subtract 0.3 again, I will get 124.4. Well, that's the bottom number on part A. So if I look at the top number on it, if I take the 125 plus 2 of those standard deviations, so 125 plus 0.6 gives me 125.6, that's looking at that range that we're wanting. This is telling me I need to be 2 standard deviations away. If I'm 2 standard deviations away, what percent captures that? 95% of the values are within 2 standard deviations. So we've got 95% of the values in that first part. Now if we go to part C, where we're 124.1 and 125.9, how many standard deviations are we away now? Okay, we're at 3 standard deviations, which is your 99.7. Questions on doing that? Chebyshev theorem. We'll talk about Chebyshev's theorem next time. Chebyshev works when you do not have things that are nice normal distributions. There's a lot of times that things are not normal distributions, and needing to be able to figure out what to do with it from there. And we'll look at the coefficient of variation next time. I need to give you the Super Bowl worksheet, but let me cut off a couple of problems first. I think number 35 is the only one I got to cut off. No, it's not a difference at all. So 35 is the only one I'm not going to assign to you guys today. On this typical Super Bowl score worksheet, don't include yesterday's scores on this, because I have not redone this with the change of yesterday's scores. Actually, I guess I don't even have last year's on this one. So don't add any other things, just use what's there. But you should be able to answer all the questions on here now. And is there anybody that does not have the project? Yes, the worksheets due Wednesday, with the Super Bowl worksheets due Wednesday. And so is the homework, yeah. The worksheet's not as bad as it looks. I mean,